Hey everyone, welcome back to Linear Algebra. This is going to be lecture 21 of the course. And in this section we're going to talk about linear transformations some more. In particular, we're going to talk about how linear transformations can be encoded as a matrix. Okay, so let's go ahead and jump into it. We'll call this section 5.2 the matrix of a linear transformation. Okay, so in this section, what we're kind of interested in seeing is the way in which a linear transformation is determined by its effect on a basis. So say I've got a linear transformation L from a vector space V into another vector space W, and I've got some basis for V. What we want to do is we want to see what happens to the basis for V when I subject it to this linear transformation L. Okay, so if we have an ordered basis for V and an ordered basis for W, in this section we're going to see how L can be encoded in a matrix, useful for examining these bases and their changes under L. Right, so we will see how L impacts a basis for V and a basis for W. Okay, let's start with an example. Okay, just to kind of gear up for some of this. Okay, let's start with an example. Let's let B equal this basis for R4. So we'll have 0, 4, 0, 1, and negative 2, 5, 0, 2, and negative 3, 5, 1, 1, and negative 1, 2, 0, 1. Okay, so this is a basis for R4. Let B be a basis for R4. Well, it turns out it is a basis for R4, so we're not just going to need to assume it. And then let's let L be a linear transformation from R4 to R3. Okay, so we'll let this be a linear transformation. And then here's how what we're gonna do is we're gonna start by just describing what this linear transformation L does to these basis vectors. Okay, so we'll say, I'm just gonna write these out. So 0, 4, 0, 1 is equal to 3, 1, 2 under this linear transformation, and negative 2, 5, 0, 2 is equal to 2, negative 1, 1 under this linear transformation. And the third basis vector, negative 3, 5, 1, 1, is equal to negative 4, 3, 0 when we apply L to it. And then the last one, negative 1, 2, 0, 1, that's equal to 6, 1, negative 1. Okay, so we can use the values of L on B to compute L for other vectors in R4. Okay, so we can use the values of L on this basis on this ordered basis B to compute L for other vectors in R4. All right, so other vectors in the domain R4. So for example, let's let V equal negative 4, 14, 1, and 4. Okay, and so we can, just using, kind of solving a system, we can calculate we can do a coordinatization of V according to this ordered basis here, right? So we can calculate V coordinatized in B And it turns out that's equal to 2, negative 1, 1, 3. Now, how did I get that? Well, just for just to make sure that we're on the same page, we know what this is. How did I get that? Well, I solved this system. I just solved the system, right? So this is going to be equal to A times 0, 4, 0, 1 plus B times negative 2, 5, 0, 2 plus C times negative 3, 5, 1, 1 plus D times this guy, negative 1, 2, 0, 1, right? Okay, and so you can just solve that. You can use an augmented matrix and row reduce it. Okay, so, but yeah, just so you know where that came from, right? So this coordinatization. Okay, and so I've got a vector v, and I can coordinatize it in this along with respect to this ordered basis b, and that's what you get when you do that operation for this specific example here. Okay, so then, right, if I want to perform the linear transformation on v, I can think of that as performing the linear transformation on this coordinatization of v, right? So that's a linear transformation of 2 times 0, 4, 0, 1 minus 1 times negative 2, 5, 0, 2 plus 1 times negative 3, 5, 1, 1 plus 3 times negative 1, 2, 0, 1. Okay, right, so this is just what v is equal to. V is equal to this, and so I just kind of substitute that in there. All right. And we know that linear transformations, when you're taking a linear transformation of a linear combination like this, I can break this apart, right? And so that's equal to, it's equal to 2 times the linear transformation of 0, 4, 0, 1 minus 1 times the linear transformation of negative 2, 5, 0, 2 plus 1 times the linear transformation of negative 3, 5, 1, 1 and then plus 3 times the linear transformation of negative 1, 2, 0, 1. Okay, and then of course these we can figure out what these are really quickly, right? We actually already did it, right? If you were to look back, we did this we kind of started with the assumption of what these basis vectors would be under this linear transformation. That's kind of how we define the linear transformation. And so we saw that the linear transformation of 0, 4, 0, 1 was equal to 3, 1, 2. And the linear transformation of negative 2, 5, 0, 2, the second basis vector, was equal to 2, negative 1, 1. And this guy here, under the linear transformation, was negative 4, 3, 0. And finally, the last one was 6, 1, 1. 6, 1, negative 1. Okay, and so altogether, this was 1890. This is 1890. Okay, so in general, if v is a vector in R4, in general for this linear transformation, if v is a vector in R4 and we can coordinatize v with respect to the basis b, ordered basis b, as k1, k2, k3, k4, then the linear transformation of v is equal to k1 times 3, 1, 2 plus k2 times 2, negative 1, 1 plus k3 times negative 4, 3, 0 plus k4 times 6, 1, negative 1, right? That's what we saw up here. And so now I'm just saying in general, given any vector in v, it'll have this same form, right? And so that's equal to, we can just kind of combine this and we get 3k1 plus 2k2 minus 4k3 plus 6k4. That's the first component, so it's basically taking the top row here. Now the middle row, would give you k1 minus k2 plus 3k3 plus k4. And then the bottom would be 2k1 plus k2, and then that's 0k3, so we'll leave that off, and then minus k4. Right, and so this is a vector. And this, what does this vector do? Well, it expresses the effect of L on the basis B. So this vector expresses the effect of L on the basis B. Oops, sorry about that. So this vector expresses the effect of L on the basis B. Okay. And so that's the idea. That's the idea behind this section. Okay, and so this example is really it's really illustrative of the next theorem, right? So frequently the theorem will come first and then you do an example. In this case, we kind of built up the idea of the theorem in this example. And so let's state the theorem that we just used. So we'll let B equal v1, v2, dot, 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 vn. And this is going to be an ordered basis for a vector space B. Okay. We're going to let W be a vector space. We'll let W be a vector space and let W1, W2, dot, 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 Wn be any n vectors in W. Okay, they're going to be any n vectors in W. Okay, so it's the setup. So I've got an ordered basis B for a vector space V. I've got W, a separate vector space with any n vectors selected from W. Okay. Then here's the sort of the result. Then there is a unique linear transformation. There is a unique linear transformation L from V to W such that L of V1, you take the first basis vector, it's going to be equal to W1. L of V2, the second basis vector, is going to be equal to W2. So on until L of Vn, which would be equal to the nth vector. So you take the nth basis vector and we'll run it through this linear transformation and you get Wn. Okay, so what's the idea here? So given an ordered basis B, right, for V, and any n vectors from W, it is possible to identify a unique linear transformation L such that each of these n vectors chosen from W can be written as a transformation of the n basis vectors. Okay. Right, so this is kind of the setup. This just shows you how this just shows you how versatile linear transformations are, right? So if I start with an ordered basis for a vector space and I have a separate vector space with any n vectors chosen arbitrarily, then it's possible to create a unique linear transformation that maps each one of those basis vectors to each of these other n vectors from W. Okay, so our next goal, given that, our next goal is to show that any linear transformation you can think of can be represented essentially by matrix multiplication. So any linear transformation can be represented by matrix multiplication. that might seem remarkable. It should seem kind of remarkable. We've seen some pretty weird linear transformations, but it turns out any of the examples we've seen thus far can be converted into simply a matrix multiplication problem. Of course, the trick is in finding the matrix that'll do that. Okay, so let's similar to what we just did, let's kind of build this up through an example. So let's recall our first example. Okay, so recall our first example. This was L from R4 to R3. Okay, we were given an ordered basis B, which was 0, 4, 0, 1, negative 2, 5, 0, 2, negative 3, 5, 1, 1, and negative 1, 2, 0, 1. Okay, so this is our ordered basis from the previous example. And we, again, remember we let V be any vector in R4. And then we said the coordinatization of V under B, we used K1, K2, K3, K4 as our notation for that. Okay, and what we saw was that V, when we apply the linear transformation to V, it's equivalent to calculating the following: 3 times K1 plus 2 times K2 minus 4 times K3 plus 6 times K4. And then we said K1 minus K2 plus 3K3 plus K4, and then 2K1 plus K2 minus K4. Okay, so we got this 3 vector here. Okay, right, so this is kind of what we had in that previous example, just recapping that. Right, so we've got linear transformation R4 to R3. Here's the ordered basis for R4. If V is any vector in R4, then a coordinatization of V will have the form K1, K2, K3, K4, and the effect of the linear transformation on V will be the following. It'll have this effect on the basis. Okay. Now let's consider the standard basis. Okay, consider the standard basis, and we'll call it C, of course, and that's just, of course, E1, E2, E3. Okay, and so this is going to be the standard basis, obviously, for R3. So now we're switching to the codomain R3. Okay, so when you're thinking about this, keep in mind that the C coordinates of vectors in the codomain are the same as the vectors themselves. Okay, so keep in mind, because this is the standard basis, right? So keep in mind that the C coordinates of vectors in R3, right? In this case, R3 is the codomain. They're the same as the vectors themselves. Right? Nothing mysterious there. I mean, just remember, like, if you had, so e.g., if I have the vector 1, 2, 3 in R3, that's equal to 1 times 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0, 1. That implies that the coordinatization of 1, 2, 3 under C is 1, 2, 3, right? So 1, 2, 3. So that's all I'm saying here. Just make sure you're kind of clear on that. So what does that mean? Well, it means that if I take V and I apply L to it, then I get L of V coordinatized under C, right? And that's because it's a standard basis. Okay. All right, so notice that. All right, so notice that if A sub BC is equal to 3, 1, 2, 2, negative 1, 1, negative 4, 3, 0, 6, 1, negative 1. Okay, these are basically taking the basis vectors that we saw previously. So these are the basis vectors of B, and coordinatizing them, switching them over to C. Then ABC is equal to, oh, I need to switch lines for this. I need a little more space. Then ABC is equal to K1, K2, K3, K4, which is itself equal to 3K1 plus 2K2 minus 4K3 plus 6K4, and then K1 minus K2 plus 3K3 plus K4, and then 2K1 plus K2 minus K4, right? So this is the transformation of V, right? Under this existing basis, 3, 1, 2, 2, 1. So you can see 3, 1, 2, 2, negative 1, 1, 2, negative 1, 1, 4, 3, 0, 4, 3, the 0 is gone, 6, 1, negative 1, 6, 1, negative 1. Right? And so hence what we can see here is that this matrix A, it contains all of the information needed, right? So this guy right here contains all of the information needed for carrying out this linear transformation with respect to, the bases that we're looking at, B and C in this case, right? So this is the matrix of interest here. This is the matrix of interest. This is the matrix that encodes the linear transformation. It takes it has all the information needed to carry out this linear transformation with respect to the chosen bases B and C, right? So we've chose B. We have a basis vector B for an ordered basis vector, or ordered basis for the domain R4, call it B, and we have an ordered basis for the codomain R3, call it C. Then this guy right here is the link between those two under this linear transformation. Okay, and so let's look at the theorem for this. Let's look at the theorem for what this guy is here. So we're going to let V and W be non-trivial vector spaces. Okay, let V and W be non-trivial vector spaces. We're going to let the dimension of V be n, and the dimension of W be m. Okay, so you've got n-dimensional and m-dimensional non-trivial vector spaces. Okay, we're going to let B equal V1 through Vn. Be an ordered basis. Well, we're going to have two of them. We're going to have an ordered basis for V, that's B, and we're going to let C equal W1 through Wm be an ordered basis. Well, so be ordered bases for V and W respectively. Okay. All right. Let's let L be a linear transformation from V into W. Okay. Then, so this is the setup, right? Let's make sure we're clear here. So V and W are vector spaces. V has dimension n, W has dimension m. We're going to let B be the n ordered basis for V. and we're going to let C be the M ordered basis for W. Okay, L is a linear transformation from V to W. Okay, and so then, here's the theorem, then there is a unique M by N matrix, and we're going to call it A sub BC, such that A sub BC times any coordinatization of a vector under B is equal to the linear transformation of V coordinatized in C. Okay, and this is going to be for all vectors V in the domain vector space V. Okay, so given two vector spaces and a linear transformation between the two, if I have an ordered basis in one and an ordered basis in the other, then this matrix ABC, A sub BC, is going to be the link that transfers the coordinatization of the vector in the domain basis to the coordinatization of the vector under L in the domain, or the codomain basis, C. Okay, and so what is this matrix here? What is ABC? So for 1 less than or equal to I less than or equal to N, the ith column of A sub BC is given by, it's going to be given by, take the ith basis vector, apply L to it, and coordinatize it in C. Okay. All right, so that's, I realize that's very kind of a complicated theorem, right? But what's the idea? Well, the idea here is that A sub BC times the coordinatization of V with respect to B, right? A sub BC times the coordinatization of V with respect to B is going to give you the coordinatization of V under L with respect to the codomain basis C. Okay, so this theorem, basically establishes that once an ordered basis for V and W has been selected, then each linear transformation is equivalent essentially to multiplying by some unique matrix, and that matrix is ABC in this case. Okay, so the matrix ABC is usually referred to as the matrix of the linear transformation. The matrix A sub BC is called the matrix of the linear transformation. Right, and frequently someone, to be more precise, we might say the matrix of the linear transformation L with respect to B and C. So it's the matrix of the linear transformation L with respect to B and C, right? B being the ordered basis of the domain, and C being the ordered basis of the codomain. Okay. All right. So this is kind of the idea. So just kind of thinking about what this theorem says, how would we go about finding this matrix ABC? And we'll spend a lot of time on this in a second, but how would we find this? How to find ABC? And it's one of those things that's frequently easier said than done. It's not always like totally trivial to find these, but in theory, the property there's a clear pathway to finding them. And here it's basically a two-stepper, right? The first thing is to find the image I want to find the image of each domain basis. Domain basis vector vi. Okay, and all that basically means is apply the linear transformation to each basis vector in the domain. So i.e. find L sub vi, L of vi for each I. Okay. That's the first thing. So you'll get you'll basically transform each of your basis vectors under L. Okay, each of your domain basis vectors. And then what you want to do is you want to express these images in C coordinates. Okay, to get the respective columns of ABC, A sub BC. Okay, right, so A sub BC is equal to L sub V1 L sub V2 dot 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 L sub Vn, right? Each of these expressed in C. Okay, so that's the idea of finding this matrix. Okay, now there's a proof of this theorem. Obviously the theorem's been proven, but you can, I'm going to encourage you to go look at the proof yourself. It's not that I mean, this whole section is a little bit tricky, right? There's no question about it. I would encourage you to go take a look at the proof. You can easily find it on, you can just easily Google it. You know, if you were to Google proof of the existence and uniqueness of matrix of a linear transformation, you would easily be presented with lots of different proofs of this. I'm going to skip it just in the interest of time, but I do recommend you take a look at it. It is somewhat enlightening. It kind of tells you a little bit more, a little bit better explanation of what's happening here and why. But I want to jump into an example. I'm going to do a handful of examples here. So let's talk about kind of a simple linear transformation, and that's going to be the reflection. So given a reflection in R3, okay, so I've got, let's just call it an L1, we'll name that's the linear transformation, and it's a R3, obviously to R3, right, and given by L1 of, I take some R3 vector, A1, A2, A3, then what's going to happen is it's going to reflect it so that I have A1, A2, negative A3. And so this is going to reflect it across the XY plane. So what is the matrix of this linear transformation? What's the matrix of this linear transformation? Well, and we're just going to say with respect to the standard basis vector. Okay, so if I was going to coordinatize this here using the standard basis vector, I could say something like this: A1, A2, A3 is equal to 1 times E1 plus 1 times E2. Oh, sorry, that should be a negative, right? Minus 1 times E3, right? And so that implies that A1, A2, negative A3 coordinatized under the standard basis for R3 would be equal to 1, 1, negative 1, right? So it's right there. Okay, and so I can easily come up with if I'm looking for my ABC, I know that that's going to be L1, E1 oh, sorry, this is not my ABC yet, sorry. So L1E1, L1E2, and L1E3. Right, I know what those are. That's going to be 1, 0, 0, and then 0, 1, 0, and then 0, 0, negative 1, right? Okay. And so, right, so this gives us what we need, right? This gives us what we need. This, given a random vector in R3, so given a random vector in R3, we'll say V equals 3, negative 4, 2. We can easily identify the effects of the reflection using this matrix. You can easily identify the effect of the reflection using this matrix. Okay, how would we do it? Well, we would just multiply, right? So 1, 0, 0, 0, 1, 0, 0, 0, negative 1, times this guy here, 3, negative 4, 2. Well, that's now equal to 3, negative 4, negative 2. Okay, which of course matches what we would expect here. The first two coordinates stay the same, the third one flips signs, and that's what you get here. Okay, so this was kind of a contrived example, and one of the things about this one is that the codomain basis of choice is the standard basis. And so that's partly why this looks a little strange up here. Normally we would do this. And it's not wrong to do that in this case. It's just that we know that the coordinatization of L1E1, for example, is just L1E1. Right? Because we're talking, C is the standard basis. Right? So let's do another example where we kind of make it a little more interesting. So we'll kind of build on some of these examples. That one was a little bit more straightforward. Let's talk about one that's... So in some cases, like, it's the process is a little clearer when you actually look at more complex bases and whatnot, and so we're going to kind of build towards that. But in some sense, it's easier to look at the standard basis, although you lose a little bit of the structure because things kind of are trivial, and so it's not as interesting. But let's take a look at this one. Let's find the matrix for the linear transformation L from P3 to R3. Okay, so P3 being the vector space of polynomials of degree 3 or less. Okay, so this is going to be a linear transformation from P3 to R3, and we're going to say it's given by, and I'll write it down here, L of A3x to the third plus A2x squared plus A1x plus A0. Right, so this is the form of any polynomial in P3. And it's going to be equal to A0 plus A1, and then 2 times A2, and then A3 minus A0. Okay, so you get a vector in R3 that is determined by the coefficients of the polynomials here. And so let's think about what is the standard basis. We'll let B be the standard basis for P3, which we know is x cubed, x squared, x, and 1. Okay, so that's a standard basis for P3, and we'll let C equal the standard basis for R3, which is E1, E2, E3. Okay. Okay, so what we're interested in is finding the matrix for this linear transformation. Okay, so this again is the matrix, or this is the ordered basis for P3, and this is the ordered basis for R3. And we've got this linear transformation, L which does this to the vectors in P3. Okay. So how do we go about finding A? We want to find A sub BC. This is the matrix for the linear transformation from B to C. And so how do we do that? Well, we first need to plug in the domain basis into L and figure out what each of those is equivalent to under L, right? So find L of V for each V in the ordered basis B. Right, so we can do that. L of x cubed. Right, so x cubed is just there's an A3. So this is 0 plus 0, 2 times 0, and then 1 minus 0. Right, so it's 0, 0, 1, isn't it? What about L of x squared? Right, x squared is a second vector in the basis for P3. Well, x squared is just going to have an A2, right? So it's 0 plus 0, 2 times 1, 0 minus 0. So that one is going to be 0, 1, 0. Oh, sorry, 0, 2, 0. So 2 times 1. What about L of x? Well, x is just going to have an A1, right? So I've got a 1 here. So 0 plus 1, 2 times 0, 0 minus 0. Right, so that'll be 1, 0, 0. And finally, the last basis vector is just 1. And so what do I get here? I get 1 plus 0, 2 times 0, 0 minus 1. So I get 1, 0, negative 1. Okay? And so this is this is the effect on the domain basis, right? Right here. So this is what you get when you apply the linear transformation to the basis vectors in the domain. Now, since we're using the standard basis for R3, each of these images in R3 is its own C coordinatization, right? So because we are using the standard basis, E1, E2, E3, these four have the same coordinatization as their face value. Right? This is again that same idea, right? If I take 0, 0, 1 and I coordinatize it in as E1, E2, E3, I get A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. And so I know that A must be 0, B must be 0, and C must be 1. Right, so that's what I mean. So this is the same, right? They're the same. And all that means is that L of V I coordinatized in C is equal to L of VI. Right, so they're the same. Okay. Okay, and so the matrix A, the matrix for the linear transformation is going to be equal to, now we know that in general it's this, it's L V1 coordinatized in C, and then it's L of, I guess I should put the actual thing, so this would be x cubed, and then L of x squared coordinatized in C, and then L of x coordinatized in C, and then L of 1 coordinatized in C, right? But because C is the standard basis, we can simplify this sum and just say L of x cubed, L of x squared, L of x, L of 1, right? Because of what I just said right here, right? It's because of that. These are the same, these are the same, same. Right, and so we could just plug them in. And what do we get? We get 0, 0, 1, right? These are just found up here, 0, 0, 1, 0, 2, 0. And then 1, 0, 0, and then 1, 0, negative 1. Okay. And so this is the matrix, the matrix for the linear transformation. Right. This is our candidate right here. This is what we're looking for. Okay. And what we can do is we can use this to calculate so we could take an arbitrary vector in the domain, in this case P3. We can multiply it by this matrix and get the resulting vector from the codomain, in this case R3. All right, so let's try that. Let's see what happens. Okay, so let's try this. We'll compute L of, let's take just an arbitrary polynomial, third degree or less, 5x cubed minus x squared plus 3x plus 2. Right, we'll compute what this is using this matrix. Okay, now we could go back to the definition of L and run it through, but the whole point of this theorem, this section, these examples, is that, hey, now we don't have to do that. We can just multiply it by this matrix we found. Okay, so let's coordinatize this. You start by you're always multiplying by the coordinates, right? So basically 5x cubed minus x squared plus 3x plus 2 coordinatized in B is of course equal to 5, -1, 3, 2. Right? And so what that means then is that L of this guy coordinatized in C is just going to be that ABC matrix times this coordinatization in B. So this is kind of a abstract here. But what we're really going to do is we're just going to basically take 0, 0, 1, 0, 2, 0, 1, 0, 0, and then 1, 0, -1. We're going to multiply it by this. 5, -1, 3, 2. And what do we get? 5, -2, 3. Right, so you can do that math. So it'd be 0 plus 0 plus 3 plus 2. That gets you the 5, right? You can just do that multiplication. Okay. All right, and so since C is the standard basis for R3, we clearly know we know then that L of this guy here, 5x cubed minus x squared plus 3x plus 2, is just equal to this, 5, -2, 3. So that linear transformation takes this third degree polynomial and converts it into this 3 tuple. Okay. All right, and we could how would we verify this? Well, we could verify that by going back to the definition, which was this guy right here. Right? We can go back to this definition, right, and you could plug in that vector and see where it all lands, right? But all we did was we just used this very nice simple matrix multiplication. Okay. Now, in this case, the codomain basis was the standard basis. So let's try the same kind of idea here, except let's apply it to a linear transformation, same linear transformation actually, but different bases. So we'll find the matrix. We'll next find the matrix for the same L, P3 to R3, R3, but with respect to different ordered bases. Right. So the bases don't matter, right? The linear transformation is the linear transformation, but if you want to encode it into a matrix, the bases that you choose will dictate what the matrix looks like, right? But the key here is that if I choose a different ordered basis for P3 and a different ordered basis for R3, then I'll get a different ABC matrix, but I should get the same answer. Like, so for example, if I run this through my new ABC matrix, I should get the same, it should correspond to the same vector in the codomain, even under this different matrix, and that's what we're going to show quick. All right, so let's let our domain matrix, our domain basis be x cubed plus x squared, and then x squared plus x, and then x plus 1, and then just 1. Right, so a more complicated basis. Right, before it was the standard basis for P3, which was x cubed, x squared, x1, and now we're doing something different here. And then let's let the ordered basis for E equal, and this is R3, instead of the standard basis, let's make it -2, 1, 3, and then 1, -3, 0, and then 3, -6, 2. Okay. Okay. All right. So we've got two different bases now. And now let's remember what the linear transformation does. So L takes a polynomial, a3x cubed plus a2x squared plus a1x plus a0, and takes basically the coefficients of this polynomial and writes them into this form. a0 plus a1 is the first component, and then 2 times this a2 component, and then a3 minus a0 is the third component, right? And so this is from P3, and this, of course, is from R3, right? So we're writing into that from one to the other. That's what this function is. That's what this linear transformation does. Okay, and so what we want to do is we want to find the matrix of this linear transformation, but with respect to these more complicated bases. Okay, so what do we do? Well, first thing we need to do is take each of the basis vectors and run them through the linear transformation, right? So we first need to find L of V for each V in D. Okay, so let's do that. So we'll start with L. We'll start with the first basis vector in D, which was x cubed plus x squared. And so when we run this through the linear transformation, now remember what this is going to do is it's going to be equal to a0 plus a1, 2 times a2, and then a3 minus a0. Right, and so this is a3 is 1 and a2 is 1. Right, so up here you got 0 plus 0. Here you've got 2 times 1. And down here you've got 1 minus 0. And so what do you get? 0, 2, 1. Okay, and so that's how that works. And we can do the same thing for all of the remaining 3 basis vectors. And for this one we get 1, 2, 0. Pause the video and make sure you're getting these same answers. And then for the next one, x plus 1, we get 2, 0, negative 1. And then for L of 1, we get 1, 0, negative 1. Right, so we got this guy, this guy, this guy, that guy. Those are our four vectors. Okay, and so next what do we got to do? Well, we got to take each of these 4 and find the E coordinatization. Right, so next we find the E coordinatization of each of these. Right, and so basically what's that entail? Well, to do that we got to solve 4 systems, don't we? Yeah, we have to solve 4 systems. And so kind of to expedite that definitely feel free to solve those 4 systems. But to expedite that, what I'm going to do is I'm going to find the inverse of the transition matrix from the standard basis C to E. Right, I'm going to call that Q. Okay, and so Q is going to be, you take the transition matrix from the standard basis C, to the basis e, and so that's going to be negative 2, 1, 3, and then 1, negative 3, 0, and then 3, negative 6, 2. Okay, so these are the basis vectors, right? If you flip back to the beginning here, we define E as, this is the basis vector. So I take those basis vectors, plug them in here, and I really need the inverse of that though, right? And so here you can do a little bit of work, right? You just have to, plug this into an augmented matrix and identify the inverse of this. But it's not too difficult to find that inverse. And when you do, what you get is negative 6, 16, negative 9, and then negative 2, 5, and 3, and 7, negative 9, 5. All right, so that's Q. So then, multiplying Q by each of the images that we got up here, each of these are the images. If we multiply Q by those images, we get the coordinatization that we're after. Okay, so let me do this kind of slowly for the first one. So if I take L of x cubed plus x squared, what I'm interested in is the E coordinatization of that, which is going to actually be equal to Q, this inverse of the transition matrix, times that 0, 2, 1 that we got up here. Right, and so that's basically this matrix here times this 3 vector, and what do we get? We get negative 1, 1, negative 1. And I can do the same thing for the others. So L of x squared plus x coordinatized in E is equal to Q times 1, 2, 0, which is negative 10, 26, and negative 15. And L of x plus 1 coordinatized in E, that guy is equal to Q times 2, 0, negative 1, which turns out to be, and again, take your time, multiply a couple of these through, make sure you see that this is working. That's negative 15, 41, 23. And finally, L of 1 coordinatized in E is Q times 1, 0, negative 1, which is negative 9, 25, and negative 14. Okay, so these 4 here are the columns of our matrix of the linear transformation, ADE. So ADE, A sub DE, is just going to be equal to this, and this column bind. Negative 1, 1, negative 1, negative 10, 26, negative 15, negative 15, 41, 23, and negative 9, 25, negative 14. Okay, so that's that. Now, what we should be able to do then is we should be able to use this matrix to calculate the effect of the linear transformation on that same polynomial that we used in the previous example. Okay, so let's compute L of, again, same polynomial, 5x cubed minus x squared plus 3x plus 2 using this matrix. Okay. So first, so because the basis is more complex, first we need to represent this polynomial using D. Right. In the previous example, we didn't really have to worry about this too much because we were using the standard basis, and so the vector itself is its own coordinatization. But here we do have to think about this differently. We basically have to solve. What do we have to solve? Well, we take the polynomial 5x cubed minus x squared plus 3x plus 2, and we have to solve a times the first basis vector, which is x cubed plus x squared, plus b times the second basis vector, which is x squared plus x, plus c times the third, x plus 1, plus d times the fourth, which is 1. And you can, this is just basically a system that you have to solve, and you can do that. But when you do that, you get a, b, c, d equals 5, -6, 9, -7, right? And definitely go back and double check that, but that's what you get. And so 5x cubed minus x squared plus 3x plus 2 coordinatized in D is equal to this: 5, -6, 9, -7. Represent that with parentheses. Okay, and so I should be able to multiply that by the matrix I just found to convert the coordinatization to E. Right, so then, just what I just said, L of 5x cubed minus x squared plus 3x plus 2 coordinatized in E is going to be equal to ADE times this. Okay, I'm going to write this slightly differently just so I can keep track of this. Basically going to be ADE times this polynomial coordinatized in E. Or, D. D. Right, which is, of course, we just found this matrix, so it's -1, 1, -1, and then -10, 26, -15, and then -15, 41, -23, and -9, 25, -14, right? And then multiply that by 5, -6, 9, -7. When you do that, you should get -17, 43, and -24. Okay, so this is the coordinate vector in terms of the basis E. This is 5x cubed minus x squared plus 3x plus 2 coordinatized in E. Okay, that's the thing coordinatized in E. And so how do we recover the vector? How do we recover the actual R3 vector? Well, we just create the linear combination, right? So L of 5x cubed minus x squared plus 3x plus 2 is just equal to -17 times the first basis vector in E, which is -2, 1, -3, plus 43 times the second basis vector, which is 1, -3, 0, minus 24 times the third basis vector, which is 3, -6, 2. Right? Do all that multiplication, and you get 5, -2, 3, as desired. That's what you would expect to get. And of course, this agrees with what we previously saw. Perfect. Okay. Okay. All right. All right. So let's go ahead, and I think I'm going to cut the video here, and then we'll pick it up in a part 2. Okay. So we'll end here and pick up in part. We'll pick up in a part B. Okay.